Okay, let's get started. Today it's our pleasure to have Cecilia Lunardini from Arizona State University. Cecilia did her PhD in the Institute of International School of Advanced Study with Alexei Smirnov in Tbes. She later took posts in Princeton as well as Washington, Seattle before settling in Arizona. She has worked extensively on neutrinos and on a variety of topics, from neutrino oscillations to cosmic ray neutrinos, as well as supernova neutrinos. And today she's going to tell us how we can find high energy neutrinos from the tidal disruption of stars and found near black holes. Please.
Thank you. Thanks for hosting me here. It's my first visit to Texas A&M and the Mitchell Institute, and I'm already very impressed. So thanks again for having me here. So you see my title, High Energy Neutrinos from the Tidal Disruption of Stars. So this is mostly from two papers in collaboration with Walter Winter and his postdoc and student. They are based at Tbes in Germany. And I was staying with them for a 3-month sabbatical stay, and so I was funded by a German institution, and also our work was also funded by the NSF, the DOE, and some European funding. So I will start with an introduction on the status of observations of high energy neutrinos from astrophysical sources, and then propose these tidal disruption events as a possible source of these neutrinos. And first I will show how tidal disruption events can produce powerful jets, and then discuss how these jets generate neutrinos at high energies. And then I will show the calculation of the diffuse flux expected from these sources and compare it with the data we currently have to see if it's a good fit, and then finish with some discussion. So you probably heard about the Cube Detector. It's a kilometer-scale detector located at the South Pole, and for several years already now it has been observing an astrophysical flux of high-energy neutrinos. They are plotted here. This is the map of the sky in galactic coordinates. So this horizontal line is the plane of the galaxy. And this wiggle line, I don't know if you can see it, is the Earth's equator. So just to give an idea where the Earth equator is. And each point, each marker here represents a neutrino. This map is a little outdated, but it's not very different from the current one. And what you can see is that a lot of these neutrinos come from outside the galactic plane, so they are extragalactic. And statistical analysis show that although there is a little bit of a hint of a clustering, overall the data are consistent with an isotropic flux. So this is the energy distribution for the deposited energy in the detector of these neutrinos, and clearly some of them are background. We expect that. So you can see here the data, and the histograms in color are backgrounds due to atmospheric neutrinos, atmospheric muons, and you can see that there is a pretty robust excess above the highest possible background you can have, which is this magenta line, and these other lines are fits to the data. The highest energy neutrino seen so far exceeded the PeV of energy. This is also a little out of date. I think the most recent detection at high energy was 4.5 PeV. That's the record energy observed. So where do these neutrinos come from? We don't know. We don't know what the sources are. And as the IceCube accumulates more and more data, a complex situation is appearing. First of all, there are several multi-messenger searches, mostly involving cross-correlating neutrino data and gamma ray observations, which are starting to disfavor the main suspects, the traditional sources like active galactic nuclei, blazars, gamma ray bursts. And at the same time, the IceCube data have been analyzed in a different way different subsets are being analyzed separately, for example, depending on the flavor, depending on the topology, depending on the energy, depending on the arrival direction. And different subsets are showing some degree of tension with one another, which suggests that maybe different parts of the neutrino spectrum might be due to different sources. So we are getting hints that the situation is more complex than initially anticipated. And so this raises the interest in classes of objects that might have been overlooked before. For example, objects that are opaque to gamma rays, so they evade gamma ray searches, and maybe multi-component scenarios in which different classes of sources contribute. So tidal disruption events have become interesting in this context of looking for alternatives. So first of all, what is a tidal disruption event, or TDE for brevity? It's the phenomenon by which a star is torn into pieces by the strong gravitational force of a nearby supermassive black hole. So the star is destroyed, and the debris of the star are in part accreted on the black hole, and this accretion generates a flare. So it's a transient event, and these flares are important in astronomy because they in some sense illuminate the black hole. These are black holes that are normally quiet. They are not AGN, they are not active nuclei, they are quiet. So a flare is an opportunity to learn something about them. The most extreme of these flares can host a relativistic jet with a hadron content, protons or nuclei, and neutrinos are expected as a byproduct of these hadrons. So observations have given us 60 candidate TDEs, out of which 3 for sure have relativistic jets, plus a number of ambiguous observations. The smoking gun for a jet is the hard X-ray spectrum, whereby hard I mean a known thermal spectrum. Okay. So this cartoon from a paper from the 80s shows the physics in a little more detail. So we have a star which is approaching a supermassive black hole, and at some point the force due to the black hole on one edge of the star is stronger than the force on the other edge, and so basically the star is being literally ripped apart. So first it's deformed, and then it's destroyed if it gets closer than a certain critical distance. And so you will have a fan-like pattern of debris coming out of this disruption. Depending on their velocity, some of them will escape, and some of them will stay bound, and they will eventually fall down, rain down on the black hole. So in this slide, I want to be a little more quantitative on what I have just shown in the graph. So let's take a mass for the star of the order of the mass of the sun, or maybe a little less. And let's take a black hole between, say, 10 to the 4th and 10 to the 8th solar masses. And one thing which is important is this critical distance from the black hole where the star can be ripped apart. And this is the so-called tidal radius. You can estimate it easily if you just assume as a condition that the black hole force, the effect of the black hole is basically comparable to the effect of the self-gravity of the star. And the result is this is the radius of the star, the ratio of the masses to the power 1/3. And if you plug in typical numbers, solar mass, solar radius, 10 to the 6 solar mass black hole, you get something like 10 to the 13 centimeters. We can compare this length with another interesting length, which is the Swatching radius of the black hole. That's the formula here, and for the same parameters, it's a few 10 to the 11 centimeters. So the Swatching radius is smaller than the tidal radius, or not, depending on the black hole mass. in order to have tidal disruption of a star, we need to have that the tidal radius has to be larger than the Swatching radius, because if that's not the case, the black hole will just swallow the star whole without disrupting it first. And this gives an upper bound on the black hole mass, which is a few 10 to the 7 solar masses. So smaller mass black holes are more effective in disrupting stars than the bigger mass black holes.
So your tidal radius formula, that assumes a circular orbit, right? Is that just you don't care about anything different because it's sort of just an approximate calculation of the station?
Yeah, I don't think there is an assumption on the orbit. I think it's just you take your star, you put it at a certain distance from the black hole, and you compare the force due to the black hole, the differential force due to the black hole with the star's self-gravity. And if these are comparable, then you say, well, the black hole is powerful enough to disrupt the star. But there might be considerations on the rotation of the star and the orbit. Yeah, if you want to maybe do a more.
But like all that stuff is like too complicated for your estimates.
Yeah, this is just order of magnitude. Yeah. So as I was saying, part of the debris of the star will remain bound, a fraction, say about half of the total mass of the star, and they will fall back on the supermassive black hole. So between the time of the disruption and the time where the flare begins, there's a dark period, which is the time where the debris take to go back, fall back down on the black hole. And then the flare begins. This plot shows the mass accretion rate as a function of time. And the idea is that you will have a peak in the mass accretion rate, and then this will gradually decrease as a power law of time. And when does this flare fade? Well, a reasonable condition is to assume that the flare will fade when the mass accretion rate will be below the Eddington luminosity, which is kind of a characteristic astrophysical parameter that maybe I can elaborate on if there are questions. But it's kind of a reasonable condition here, and that's what this line is. And by equating these two rates with reasonable parameters, you find a duration of the flare between a month and a year, or a few years. So these are long transients, as opposed to, for example, the gamma reverse, which are a few seconds long. These are years long, or months. So this graph shows the best known TDE with a jet. A jet TDE was observed by Swift a few years ago. It's called Swift J1644. And is the TDE prototype that everybody uses. So here is in green is the luminosity, okay, in sort of scale units, and on this axis is time in seconds. So you see that this is X-rays, okay. So the luminosity is kind of irregular, and then it becomes a little bit more regular later on. This was at a distance of 1.8 gigaparsecs, redshift 0.35. It had a hard X-ray spectrum, which is the indication of a jet being present. And this energy spectrum of this X-ray photon flux had a power law with a break in the spectrum around a K. For the purpose of estimating the jet, the physics of the jet, an important quantity is the minimum variability time scale. So the smallest time scale over which there is a significant luminosity variation, and that was measured to be about 100 seconds. And the total duration of the flare before it faded was of the order of 10 to the 6 seconds, so about a month, in line with the theoretical expectations. And the Lorentz factor of the jet was estimated roughly to be of the order 10 from the Swift data. So in our work on neutrinos, we used parameters which are here in blue in this table, which match those measured by Swift for this particular TDE. I didn't mention this one. EX is the isotropic equivalent energy in X-rays. 3 × 10⁵ ergs, is the same as of a supernova. And alpha and beta are the power laws of the X-ray spectrum, 2/3 and 2. And then the parameters in black are theoretical parameters that couldn't be inferred from observations. This is the proton spectral index, 2, so we are assuming an e⁻² proton spectrum, which is pretty reasonable for a Fermi acceleration type of phenomenon. And then we have these two parameters, the baryonic loading, the magnetic loading. These are the energy in baryons and the magnetic field relative to the energy in photons. And these are theoretically motivated parameters. So before I move on, some references. The theory of TDEs is pretty old. It goes back to the 70s. I strongly recommend this paper by Martin Rees. And then as the theory evolved, there are newer papers which are more numerically oriented. So the older papers are really order of magnitude kind of work, which I really like. The newer papers are more numerical, simulations and plots, lots of plots. Observations are very important. And then starting in 2009, there were some papers pointing out that the jets generated by a TDE can accelerate protons to ultra high energy. So they can be sources of ultra high energy cosmic rays. And if that's the case, then we know that cosmic rays produce neutrinos as a byproduct. So we should also have high energy neutrinos. And there is literature on this. And there has been a bit of a renaissance of this topic in the past couple of years. So let me now talk about neutrinos from a tidal disruption event. So what we did here in our work, and what everybody in this field does, is to not address why a jet forms. We assume that there is a jet with certain parameters consistent with observations, and then we study how neutrinos are generated in this jet. And so the classic scenario for this type of jets is the so-called internal shocks. So what we have an internal emitter, a central engine that ejects relativistic chunks of plasma. And clearly, all these blobs of plasma will have a certain velocity distribution. Some of them will move slower, some of them will move faster. So it's expected that two shells will eventually collide, and it's in this collision region that a shock is produced, and a shock can generate, through the Fermi mechanism, can accelerate particles to very high energies. So if we imagine having very high energy protons produced here, these protons will interact with the photons in the collision region. There will be photons living in this collision region, and this will produce pions. And pions generate neutrinos through a two-step decay chain, pion decaying into muons and neutrinos, muon decaying into electron and neutrinos. So for each pion, we expect to have 3 neutrinos, 2 of muon flavor and 1 of electron flavor. So an accurate calculation of the flux of neutrinos from a jet, from internal shocks in a jet, is actually complicated. You have to have a code with a high level of sophistication. However, for the purpose of explaining the physics, I think it's worth looking at some analytical approximations which are very instructive. So I'm going to show this, the so-called delta resonance approximation. So this is fairly crude but effective. We are modeling the proton-photon cross-section as a Dirac delta at the delta resonance. So we assume that the entire power of the cross-section is at the point where the delta baryon is resonantly produced. And so that simplifies the calculation a lot. And here is the result. This is E squared, energy squared, times the neutrino fluence for muon and electron neutrinos. No oscillations. I'm not including neutrino oscillations yet. And here is what you get. So there is obviously a geometric factor proportional to the distance to the source, to the -2. And then this is a normalization, is the total energy in baryons, the parent proton flux. And then the key quantity here is this Fp gamma. Fp gamma is the pion production efficiency. That's where the cross-section comes into play. And you can see it's proportional to the energy of the luminosity in photons. And then there is some dependence on the time variability scale, the Lorentz factor, and the parameters of the photon spectrum. And there is this beta and alpha. If you remember, there is this. These are the powers of the photon spectrum, which are inherited by this Fp gamma. So there is this proton break energy, this parameter here, which is of order of a few 10 to the 7 GeV, and that's the energy where the delta resonance is exactly at the breaking point of the photon spectrum. Okay. So next, I'm going to spend a few words on these zeta pi and zeta mu, which model the fact that the pions and the muons, depending on the energy, the pions and the muons will lose energy as they propagate before they actually decay. And so these are damping factors, basically. And if you look at the pions, for example, there is a characteristic energy beyond which the flux of neutrinos is suppressed because the pions lose energy before decaying. And the energy losses are due to synchrotron radiation and inverse Compton, primarily inverse Compton scattering. So the zeta pi is 0 below the break energy, and it goes like e to the -2 above the break energy. And likewise for the muons, similar thing. The difference is that the break energy is higher for the pions, a few 10 to the 8 GeV, and for the muons is lower, a few 10 to the 7 G. Okay? And I'm asking you to remember that there is a strong dependence on gamma, and there is a dependence on TV, the variability time scale. So if you do the analytical approximation, what you get is this sort of choppy spectrum. This is E squared times the spectrum. Thick is for muon neutrinos, thin is for electron neutrinos, and there are three break energies here where the spectrum changes slope, and this one is due to the proton break energy, the one which is related to where the photon break energy spectrum is. And then this one is the muon damping break, and this one is the pion damping break. If you have any doubt which is which, you need to look at where the electron neutrino spectrum starts to be suppressed. That's clearly the muon damping energy, because the electron neutrinos are daughters of the muons. So that's the muon damping energy. Okay. For comparison, the smooth spectrum is the numerical one, calculated by the DAISY group with a sophisticated code, which is called New Cosma. And they have a realistic cross-section for the proton-photon interaction, and they include a number of secondary processes. And so all in all, they agree, the simple form and the numerical one, but there is a bit of discrepancy. But overall, there is a good agreement. So in our work, we calculated the flux expected for a jet with the parameters you have seen in the table a few slides ago. But we also considered that tidal disruption events can occur for black holes which have masses varying over several orders of magnitude. You can have 10 to the 7, 10 to the 6, 10 to the 5 solar mass black holes. So we expect a certain degree of dependence on the black hole mass. And that's what we try to work out here. For example, the variability time scale is important because it tells us how far out in the jet the collisions typically occur, the shell collisions typically occur. And this might be related to the black hole mass because it could be related to the Swatching time. Swatching time is what happens if you just take the Swatching radius and convert it into a time. And it also happens to be the period, it's close to the period of the innermost stable circular orbit. That's how close you can be on a circular orbit around a black hole without falling in. So it's kind of possible that the two might be related. And if you calculate the Swatching time for a typical black hole mass, you get about 63 seconds, which is close to the 100 seconds of the Swift observation. So it kind of matches. And then it's possible that the gamma factor might also depend on the mass. This is a little more phenomenological. There is this paper on AGN. So active galactic nuclei have this sort of mild dependence on the mass. We don't know how applicable this is to all black holes. And then if you take all the data from all TDEs, whether they have jets or not, then you can feed them and you will find that the X-ray luminosity also grows with mass. The best fit is of a linear form. So these are all speculations in some sense, but we wanted to see what happens if we have some of these entering the neutrino calculation. So in what follows, I'm going to show the base case, which is the one you have already seen, with all the parameters fixed at the Swift measured parameters. And then I'm going to show various combinations in which we scale only gamma with the mass, or we scale both gamma and TV, or we scale all the three of them, including the X-ray luminosity. So I want to make you reflect a little on the difference between base case and strong scaling case. So if we decrease the black hole mass, we are decreasing TV, and we are decreasing gamma, and that means that we are increasing the pion production efficiency, FP gamma, because FP gamma goes like gamma to the -4, TV to the -1. So you will have more neutrinos because you're increasing the pion production efficiency. And the spectrum of these neutrinos will be at lower energies because the break energies, the three features you have seen in the spectrum, they go like positive powers of gamma and TV, so they will all shift to lower energy. So in this case, we expect a higher flux at lower energy. And I'm not going to show the weak and the Lumi scaling because these are sort of intermediate between the base and the strong scaling. So this is the expected flux for a single tidal disruption event with the base parameters. You have already seen this. This is now including flavor oscillations and then plotting the curve only for muon neutrinos. And what I'm plotting here is the so-called flavor ratio, is the ratio of the muon neutrino flux divided by the flux of the other two flavors. And you see that there is this transition here. It's a small transition, but still. And that signals the muon damping regime. So this is the muon break energy. So that's what this transition is due to. So this is the case with the strong scaling, in which I'm scaling gamma and the time variability scale. And as I announced, if you go to lower black hole masses, this is 10 to the 7, 10 to the 6, 10 to the 5, you get a higher flux shifted at lower energy. And likewise, this is the flavor ratio. If you go to lower and lower masses, this transition to the muon damped regime occurs at lower energy. Okay? And this is interesting because IceCube is observing at PeV or less. So this can be within what IceCube can possibly probe. So we have wondered about possibly observing neutrinos from a single tidal disruption event, which would be exciting. But it turns out that this is unlikely to happen because the fluxes you have just seen for typical parameters are close or below the flux required to be detected. So individually, the chance of detecting these events is low, but we can detect the diffuse flux from all of them, and that's what I'm going to show next. What we need to calculate the total flux of neutrinos from all TDEs? Well, we need to know the volumetric rate of these tidal disruptions. So we need to know this rho dot, function of redshift and of the mass m of the black hole. And this is the number of TDEs that occur per unit time, per unit of moving volume, differential at redshift z, and differential in the mass of the black hole. So the result, and I'm going to explain where that comes from, the result is that it goes, this rate goes like 1 plus z to the minus 3, z is the redshift here, and it goes like the black hole mass to the minus 1.6, and this is not zero only if the mass is between a maximum and a minimum, where the maximum is the one you have already seen before, a few 10 to the 7 solar masses, and the minimum I'm going to explain it in a moment. So this is not zero in this interval and zero outside this interval, approximately. So where does this come from? It comes from the product of three different functions. This one, phi of Zm, is the volumetric density of supermassive black holes. So clearly, the more black holes you have, the more tidal disruptions you have. So the volumetric density is the one that gives the redshift dependence, and it gives an m to the minus 3/2 mass dependence, approximately. That's from this reference. And then there is this factor, which is called the galaxy occupation factor. This is the probability that a black hole is situated at the center of a galaxy. You need that for tidal disruption because the black hole has to be in a star-dense area. So the idea is that this occupation fraction is roughly 1 above a minimum mass and 0 below a minimum mass. So we assume that the idea is that if a black hole is too small, it's less likely to be living in the center of a galaxy. And this minimum mass is very poorly estimated. It can be a few 10 to the 4 solar masses up to a few 10 to the 6 solar masses. And then finally we have the rate of TDEs per black hole, and that's estimated in these two papers. And there is a mild dependence on the mass of the black hole. So all the three together give you this behavior. So the main really important point here is that in the rate of TDEs, what dominates here is the low redshift region of space and the low mass region of the black hole spectrum. Okay. So in this graph, you see the total rate of tidal disruptions per cubic megaparsec per year, integrated over the black hole mass, depending on the minimum mass we take. Clearly, if we take a low minimum mass, you get a relatively high rate. And if you get a high minimum mass, then the rate is much lower. And you can see here the z dependence as 1 plus z to the minus 3. Okay. So the rate, there is a change of more than an order of magnitude depending on what m min is. So to calculate the diffuse flux, what do? You take the emission, the neutrino emission of a single TDE, the function of m and function of energy, and there's z, of course, redshift should be included. Then you multiply by the volumetric rate, and then integrate over the redshift with the appropriate cosmological factors, and then you integrate over the range of masses of interest. And you have to include two parameters. One of them is this eta, which is the fraction of jetted TDEs. Not all TDEs have jets. We assume that about 10% of them do, but of course we don't know this number precisely. And then there is this factor 1/2 gamma squared, with gamma being a function of m, although this is about 10 to the minus 2, and this is the so-called beaming factor. It's it accounts for the fact that we only see neutrinos from jets that point in our direction. So because these are narrow jets, we only see basically 1% or so of them. So after doing the integral, this is what you get for the base parameters. This is now the flux of neutrinos at Earth multiplied by E squared. So it's GeV per square centimeter per second per steradian. And the shaded region is what you get if you vary m min in this interval, 10 to the 4.5 to 10 to the 6.5 solar masses. And you can see 10 to the 6, 10 to the 5. There is the strong dependence on m min. But overall, the shape is pretty much similar to the shape that you get for a single TBE. And that's because, as I said before, the low redshift region dominates. So these are mostly due to low redshift TBE, so there isn't much of a redshift effect. And also this is the flavor ratio, mu on neutrinos divided by the other two flavors, is also similar to the single TBE plot that you've already seen. This is, I'm marking here at a few 10 to the 6 GeV. I'm marking here the glacial resonance. The glacial resonance is basically when you have resonant production of the W in electron neutrino scattering. And this is something that, in principle, IceCube is sensitive to. And so it's interesting to note that for this model, the glacial resonance is below the muon damping regime. So this is the case for strong scaling. Again, the shading corresponds to the interval of m min. And you can see here the enormous dependence on m min. It's really, really big, spanning several orders of magnitudes. And here we have the the flavor ratio. And here we have for 10 to the 5 and min equal to 10 to the 5 solar masses. Then we have an early transition to the muon damping regime. And now the glacial resonance is pretty much in the muon damping region of the spectrum. So at this point you are wondering probably how well does this fit the data. So here is the answer. This is a plot from the IceCube collaboration 2015, the data. These are the data, all flavor flux, heat energy beams. And these are our predictions. The blue and the yellow one, you have not seen them before. They are kind of variations of the other two. And what we did here, this is not a fit. This is, we have rescaled our curves to match the measured flux at a PV scale. So they are all rescaled to match this point. And to rescale them, we played with the normalization factors, which are uncertain anyway. So for our parameters of reference, the normalization factor is the product of the baryonic loading and the fraction of ejected TBEs, which we took to be 10%. So this is 1, actually, for our parameters of reference. And it turns out that in order to match the IceCube flux, the strong scaling case had to be rescaled down because this was such a big predicted flux. So if we have a very modest eta or a very modest baryonic loading, we can feed the data pretty well, above say 100 TB. You can see that the other curves don't feed the data as well because the spectrum is more energetic, so it kind of peaks at higher energy, and also because we had to rescale them up by quite a lot. So we need to, in order to reproduce this point, we needed to rescale the normalization to pretty extreme values. So the red curve is clearly the one that has a chance to reproduce the data well. which is interesting. So what this might lead to is a composite scenario. We could have a scenario which is natural for a variety of reasons, which we could have a scenario in which one class of sources, for example Tbes, could reproduce the high energy neutrino events, and another class of sources could reproduce the lower energy part of the neutrino spectrum. Okay, and keep in mind that background contributes here too. So this could be a combination of background and a different class of sources.
By background, you mean atmosphere?
Yeah, atmospheric. Yeah. So just one slide or two on our latest paper on possibly reproducing neutrino data and at the same time cosmic ray data with tidal disruption events. That's really interesting. So because I have time, I can spend some time explaining what these plots are about. But basically first the punchline. The punchline is that you can find a set of reasonably natural parameters for TDEs where you can reproduce the cosmic ray data from Auger and the ice cube data in the higher energy part of the spectrum pretty well if you have a medium mass composition. So instead of having protons in your jet, if you have a medium mass nuclear composition like carbon, oxygen, nitrogen, you can reproduce the cosmic ray data. And for TDEs, we are in a regime where nuclear disintegration is very important. So in your jet, you start off with a medium mass nuclei, but then inside the jet, this nuclei will disintegrate. And so outside the jet, beyond the jet, you will have a kind of a family of nuclei that are all daughters of the primary nuclei that you injected in the jet. So application of this, what could give you a possibly medium nuclear mass composition? It could be a white dwarf. White dwarfs are have this sort of composition: oxygen, carbon, nitrogen, and so you could have an intermediate mass black hole disrupting a white dwarf, and it could give you this sort of composition. So now the plots, these are kind of small. You can zoom in a bit. So this plot, the dots are the Auger cosmic ray data. You see they go up to 10 to the 20 eV. And this is the energy spectrum. And these are also the Auger data for the so-called X-max. X-max is the depth of the cosmic ray shower in the atmosphere, where the cosmic ray shower has a maximum. Okay, and these lines, the colored lines, correspond to certain isotopes. So Auger, this was kind of a big breakthrough recently, that the Auger data favor a medium heavy cosmic ray composition at the higher energies. So you can see this is nitrogen, this is helium, iron. So at the highest energies you have this sort of medium composition. And so the brown is the TDE prediction for judiciously chosen parameters. You can see that it's pretty good. And at lower energy here we expect, this is expected because we have a different, this is where a different production mechanism comes in. So we are aiming at reproducing this ultra high energy spectrum model. And so this is probably a little too detailed to get into, but again, the brown is our prediction. It's pretty good. And this is the corresponding neutrino prediction for TDEs, for the exact same parameters. So the same parameters will give you this blue curve. This is the neutrino spectrum compared with ice cube. And they will give you the brown curve here, here, and here. Okay. And the key to have this spectrum modeled well is the nuclear cascade in the jet. These are, you start with a jet which contains only nitrogen, and then the nitrogen propagates and will generate some other nuclei. So these are the contribution of the lighter nuclei, and this is the contribution of the primary nitrogen. Okay. So I have one more slide on this, but I'm keeping it as a backup because it's a bit more detailed. And I will conclude here. So my conclusion is that tidal disruption events are an interesting class of candidate sources to look at. They haven't been examined in detail. They are interesting as neutrino sources. They are interesting as cosmic ray sources. And interestingly, they are not really well constrained. This is something I didn't really emphasize much before, but they are not seen in gamma rays. They are only seen in X-rays because they are expected to be opaque to gamma rays. So they are mid to long duration transients. That's already kind of a challenge because long transients are more difficult to look at than short transients. As I said, the photon counterpart is sub-MeV, is below gamma ray, that is more like in the X-ray spectrum. They can account for the higher energy part of the ice cube data. Well, this is maybe a bit of a technical point. There is a change in the favorable composition at PV that we can predict. It's a signature of the scenario. And so in order to constrain these TDEs, you really need a dedicated search. You need to have a dedicated search that looks at long duration transients. You need to look at the interplay with X-rays rather than interplay with gamma rays. So this is something for the future, and I know that the Ice Cube collaboration is planning search for this class of objects. And what we can learn, well, if these are the sources of neutrinos, at least in part or of cosmic rays, this would be extremely interesting, of course. But also there is the possibility to learn about black holes, because most of the black holes that we produce these TDEs are quiet black holes. So we can use these TDEs to learn about these black holes. And then the neutrino spectrum, as you learned, is very sensitive to the M-min, to the minimum mass that the black hole has to have to be an effective star destroyer. And this is something that we don't know much about. And then we can learn about the frequency of these TDEs, how often do we get the TDE with the jet. Maybe all the TDEs have jets, but we don't see them. Or maybe it's a very rare occurrence to have a jet in a TDE. We don't know. That's something we can learn about if we have more data from neutrinos and other sources and other surveys. So I close here, and thank you for your attention. Thanks.
Thank you, Cecilia. Any questions? Yes.
So I see that for the higher energy, TDEs are better fit. For lower energy, there is not much of a fit. And so when this results from Ice Cube came around, at that time, some of us from particle physics side, we tried to fit the data. And for the low energy part, it seems that we can do much better from the particle physics side. So have you ever tried to see like a combining these particle physics models which try to explain TeV along with your TDE to see whether there is a good fit?
You mean maybe by particle physics model?
Like a laptop quark model.
Exotic physics?
Exactly.
No, we haven't.
Because I see that you have two shapes, one from the astrophysics side, and particle physics side always had a stretch for the higher energy piece. I think maybe now it could be a good fit combining these two stuff.
Okay. Yeah, there is always the question, of course, what is the role of the exotic physics? Exotic, beyond the standard model.
Beyond the standard model, but then you have predictions for other experiments.
Right. Yeah, no, that would be interesting to do, but we haven't done that.
No, that's fine. Just I was wondering.
So which one you recommend?
Combination of both.
New physics.
No, actually, at that time, like Louis and I, we wrote a paper using leptoquarks, and, which can explain the PV. But it was a stretch for higher energy, and we were always wondering like what to do with that. But now we have a solution.
That is the first, second, third generation.
Yeah. So it can be a combination, flavor.
But low energy pins here are not inconsistent. They're just.
They are. Error bar is. You saw that there is a one such shape, and then there is a.
I mean, yeah. So they're not.
See, there is a point up there.
Yeah.
There is a point up there with a little error bar.
Yeah.
So you can see that's what Cecilia is saying, that there could be two shapes here.
Yeah, so my gut feeling is that clearly the universe is vast and complicated, so it's kind of natural to me that we should have more than one class of sources contributing. And in particular, I think there are basically two types of sources. If you include only standard model particle physics, you can have P gamma, proton-photon interaction, which is this one. And you can have proton-proton. And proton-proton tends to give you an e to the minus 2 form. So you can have something else, which will give you proton-proton, and then you can have, on top of that, you can have this one. And in fact, tidal disruption events, this is something we haven't done, but it's in the back of my mind. Tidal disruption events can give you something like this if you consider that the jet might propagate through some stellar debris. There might be a cocoon around that we are not including. So if you have some sort of proton-proton mechanism in addition to proton-photon, then you could have something here which will still come from tidal disruption events, just a different part of the jet propagation. So, but there might be, of course, new physics effects coming into play eventually. Yeah.
Another question. So, you have to estimate the rate of these things happening, right? And there's tens of these events in the universe. And, it's my understanding that some of these events get confused with low luminosity supernova. Like if you look at the light curves, is that kind of true? And I mean, how robust are these? I mean, you listed a bunch of papers, I think, by Kachanik and some other people who talked about estimating the rates of these things. How that probably contributes substantially to a systematic uncertainty of what this normalization is.
The confusion with maybe low luminosity.
Yeah, because sometimes whenever you hear some supernova got detected, and they're worried that it's confused with one of these tidal.
I remember. I don't have any figures that I remember, but I know some that are still debated. So these three that I listed, they are pretty robust. They are all from Swift. But there is one which I think is called Assassin 14 something. That one is still debated. So some people say it's a low luminosity supernova, some people say it's a TD. That's the source of systematics.
Okay, very quick follow-up. So, these neutrinos come from pions, et cetera, and interacting with the jet. And I mean, something similar presumably happens in gamma ray bursts, right? It's just Lorentz factors are a little bit different. I mean, so what is sort of different about the spectra of these things relative if you plot the spectrum of a gamma ray burst neutrinos from a gamma ray burst?
Right.
What are just the very, very top level physics differences? Lorentz factor, what else?
Lorentz factor is typically higher for GRBs, it's more like 100 or so. And then the GRBs are, I think they are comparable in luminosity, but they are much shorter duration. They are much shorter, so GRBs, there are these long GRBs, the short GRBs, but even the long GRBs are pretty short for this scale.
Right,
so
but it's a diffuse flux, right? Like a diffuse flux, they would look similar, right?
Well, there are already searches looking for positional associations with GRBs, because GRBs, being short transients, you can really pinpoint them more easily with timed searches. So people look for time and position coincidence of the neutrinos with GRBs. And the time window is maybe 100 seconds. so you can do it pretty well. And they don't see any. So GRBs are already disfavored by those sort of correlation searches, which haven't been done for TDs. So the length of the transient being very different means that these TDs are more difficult to probe because they are long transients. They are kind of in between. It's kind of fascinating to me how these things are in between what people commonly call transients and steady sources. So they're kind of like
long time scale.
yeah.
Any other questions? Okay, we'll have our usual coffee chats at the fourth floor discussion room. Please grab your coffee and feel free to join us. Otherwise, let's thank this room of time.